Thank you for joining today. I am pleased to introduce Professor Benjamin Stickler as today's speaker for the Non-Hermitian seminar series. And Professor Stickler's academic career is marked by many contributions to quantum physics. I will call him now an expert on levitated optomechanics, among other fields. And so he started by studying master degrees in both physics and chemistry. Is that correct?
Yes.
In consecutive years from Graz University of Technology. He obtained his PhD in 2013, also in Graz. And then he moved for a postdoc to Duisburg, Essen, where he stayed for until 2019. And then later on as a Marie Curie Fellow in Imperial College until 2020. And recently, he has started his own group as a professor, as a Heisenberg professor in Ulm, in the Institute of Complex Quantum Systems. And of course, yeah, I'm now happy to leave the floor to you, Benjamin. Whenever you're ready, please feel free to share the screen.
Okay, thank you very much for the introduction. Happy to be here. Thanks for having me. So today I will speak about our recent research on the non-reciprocal interactions and the possibility of generating and observing entanglement between optically levitated nanoparticles. As Javier already mentioned, my research focuses mainly on observing and probing and exploiting quantum physics with nanoscale objects such as levitated nanoscale dielectrics, which contain millions to billions of individual atoms, and which can be levitated and controlled with very high precision in optical tweezer traps. And in recent work, together with Henning Rudolph, who did most of the theoretical work, a PhD student at the University of Duisburg-Essen, in the group of Klaus Hornberger, and together with the experimental group, experimental team of Delić and Aspelmeyer at the University of Vienna, we investigated how two co-levitated nanoparticles, like depicted in this picture, which are levitated in the vicinity of each other and which can speak to each other via scattering tweezer photons, how they can be brought into a regime where the interaction becomes effectively non-reciprocal. So the interaction seemingly violates Newton's third law of reaction equals action, and how such an array of nanoparticles can be used for observing entanglement in mechanical degrees of freedom of levitated objects. Now, let me start with a short introduction on levitated nanomechanics. So in the field of levitated optomechanics or levitated nanomechanics, dielectric objects are typically optically levitated, where their mechanical motion, so their center of mass motion and rotational motion, can be read out and manipulated with very high precision. For optical trapping fields, the situation is relatively simple. The light field induces an internal polarization field inside of the particle. This internal polarization field oscillates with the optical frequency and leads to light scattering. And the scattered light can be recycled. It can be either detected and used for applying forces and torques via a feedback loop, or it can be recycled through an optical cavity, which then exerts optical forces and torques on the particle. And by precisely engineering these interactions, one can achieve a situation where the motion of these objects can be controlled and, for instance, cooled to very low temperatures. Levitated nanoparticles range in a big variety of different optomechanical systems, which span a huge mass regime from macroscopic mirrors as they are used in gravitational wave detectors, all the way down to single levitated atoms. And nanoparticles, levitated nanoparticles, range in a mass regime of approximately 10 to the 10 atomic mass units. That's 10 femtogram. The field of levitated nanomechanics is has recently witnessed a number of breakthroughs. I want to mention one in particular here, and that's the recent demonstration of cooling the center of mass motion of such a particle into its quantum ground state. The first demonstration used cavity cooling, but afterwards ground state cooling was also demonstrated via feedback cooling. I won't explain that in detail, but let me just briefly explain how cavity cooling works to give you an idea of how we control the motion of these objects at the quantum limit. So here you can see a small nanoparticle. That's an image of the nanoparticle. It has roughly a diameter of, it's spherical and has a diameter of roughly 150 nanometers. It's optically trapped in an optical tweezer, so a highly focused laser beam. So that's the magenta thing here. The tweezer exerts a dipole force, which traps the particle in the intensity maximum. Now, by placing a cavity around the system and by slightly detuning the tweezer frequency with respect to the cavity resonance frequency to the red sideband, one can achieve a situation where scattering of photons into the cavity that extract a phonon of motion of the particle from in the optical trapping potential is enhanced. So anti-Stokes scattering of photons is enhanced, and this enhancement of anti-Stokes scattering is referred to as cavity cooling. And by exactly balancing the cavity properties and the frequency, one can achieve a situation. Here you can see the mean occupation of the particle center of mass motion in the harmonic trap versus the detuning of the tweezer from the cavity resonance frequency. And by choosing the detuning in the right range, which is on the red sideband close to the mechanical frequency, one can achieve a situation where the mean occupation of the particle is well below 1, which means that with a high probability, the quantum state of the particle, that the particle is prepared in its quantum ground state. And that recent demonstration was achieved in the group of Markus Aspelmeyer by Rudolph Delić at the University of Vienna in 2020. And since then, a number of teams have achieved cooling to the quantum ground state, also by other techniques such as feedback cooling, where the light is detected and then recycled to apply a feedback force onto the particle. Now, these experiments are prerequisites for future quantum experiments with levitated nanoparticles. And of course, now one can ask the question, why are we interested in levitating those things at all? And usually we have 3 main reasons for levitating a particle in the first place. So a levitated nanoparticle is an optomechanical system that is extremely well isolated from its environment. In particular, a levitated nanoparticle doesn't exhibit any clamping losses. It's completely isolated. It can interact with residual gas atoms, but by evacuating the chamber, this can be reduced. And then the only noise that's left is shot noise from the tweezer. But there's 2 other reasons which I want to highlight, which make levitated nanoparticles particularly interested in comparison to other optomechanical systems. One of those reasons is the fact that a levitated nanoparticle can rotate. Now, rotations are not only novel degrees of freedom, but rotations are inherently nonlinear, which makes them particularly interesting for quantum applications. So we have been working quite a lot on controlling and observing nanoparticle rotations over the last couple of years. I will not talk about this today. We'll just give you a brief overview here. So we have been working quite a lot on how to control the rotation of nanoparticles. We have devised schemes to cool their rotational motion and combined center of mass motion into the 6D quantum ground state via variation of coherence scattering cavity cooling, which uses elliptically polarized tweezers in order to achieve 3-dimensional alignment of aspherical objects. Then we have worked quite a bit on controlling particles with embedded spin degrees of freedom. Why it's that interesting? Well, spin carries angular momentum, and this angular momentum contributes to the total angular momentum of the particle, meaning that if you flip the spin, in absence of external torques, the particle must rotate afterwards because total angular momentum is conserved. This is known as the Einstein-de Haas effect, and it can be particularly strong for small objects such as a levitated nanodiamond with an embedded NV center. Then we have been working quite a lot on how rotational degrees of freedom decohere in interaction with ambient environments, and we have been working a lot on rotational interference schemes, so quantum protocols which explicitly exploit the fact that rotations are inherently nonlinear to realize interference protocols without the requirement of having a beam splitter. If you want to know more about quantum rotations of nanoparticles, I encourage you to take a look at this recent review that we wrote, which summarizes most of our findings, and that of most of the findings in the community. Maybe just to convince you that rotations are inherently nonlinear, which might sound bit weird if you hear it the first time. So this is a video from the ISS where you can see an asymmetric rotor as it rotates freely. So that's a purely classical effect. And it shows what is known as the tennis racket instability. So it's an asymmetric rotor. So it is characterized by 3 distinct moments of inertia. And that means that rotations around the axis of intermediate moment of inertia are unstable. And that forces it to flip back and forth with a well-defined frequency, and that frequency is determined by its initial conditions. And that's the free dynamics. There's no external torques acting on the particle. This is a manifestation of the strong nonlinearity of rigid body rotations, as also manifested in the nonlinearity of Euler's equations. And in the quantum regime, these nonlinearities can lead to strong interference signals. So you can start out, you can prepare your rotor starting out with a state that is characterized by a positive Wigner function, and then without having to have external potentials, this positive Wigner function develops negativities and the particle can start interfering. And the most pronounced quantum interference effect for rotors is known as the orientational quantum revival. So that's a artistic depiction of how such a revival looks like. A rotor that is initially aligned, so it's in some thermal state, which has a mean angular momentum 0. And then it's released, it starts rotating into all directions, and then an integer multiple of the quantum characteristic revival time, it perfectly comes back. And this recurrence of the initial state is a pure quantum phenomenon, and it's related to the discreteness or the quantization of angular momentum states. So you can easily see it from the unitary time evolution operator of a linear rigid rotor, which is proportional to the exponential function of some time factor j times j plus 1. And since j is an integer because angular momentum is quantized, j times j plus 1 is always an even number, implying that if the time is given by 2 pi times moment of inertia over h bar, this is always unity, irrespective of the initial state. That's a pure quantum phenomenon. The revival time is usually extremely long. So for instance, for this pen here, it would be longer than the age of the universe. But for nanorotors on the length scale of 50 to 100 nanometers can be in the range of milliseconds. So that's observable in principle. Okay, so that was everything I wanted to say about rotors. Now let me come to the main topic for today's talk. The third main motivation for looking at levitated particles, in my opinion, is that they can exhibit strong and tunable interactions. And what do I mean by that? I will explain in the next half hour. So I will walk you through our recent works from the last 3 years on optical binding interactions, so light-induced interactions between 2 co-levitated particles. I will first present you the classical basis of these experiments and also explain to you the experimental efforts in the group of Delić and Markus Aspelmeyer. Then I will present to you our recent work on how to formulate a consistent quantum theory of optical binding and how we identified or what we identify as quantum signatures of optical binding. And then I will discuss the question whether these interactions can and how they can be used for generating and observing entanglement between co-levitated objects. All right, let's start. So most of the things, or everything that I will be telling you in the next half hour are calculations based on the PhD thesis of Henning Rudolph, whom I have co-supervised, who is at the University of Duisburg-Essen. So the situation that we are interested in is two particles. We approximate them as spherical for the moment. Each particle is illuminated by some laser field, and this laser field leads to an internal dipole moment. It induces a dipole moment because the particles are polarizable, and this dipole moment oscillates with the external frequency and leads to scattering, and the scattered light can travel from one particle to the other and lead to some interaction. So how do we describe that theoretically? What does that mean? So we induce a dipole moment in the particle J, and this dipole moment is proportional to the volume of the particle and its susceptibility, which can be a tensor for aspherical objects. But for now, let's just say it's a scalar quantity because we have perfectly spherical objects. And then it's proportional to the electric field at the center of mass position of the particle. Now, if we take into account that the total electric field at the position of the particle is not only given by the local electric field, but also by that electric field that scattered from the other particle to the particle that we are interested in. So then we get this additional contribution, which scales with the susceptibility squared, with the volume of both particles. Then this here is the electromagnetic Green's tensor, which describes the field propagation from particle 2 to particle 1, and the electric field that is present at the position of particle 2. Now we can use this induced dipole moment to calculate the optical force acting on particle 1 and particle 2. And if we do that, we obtain this complicated expression. Now let me walk you through this. The total force acting on this particle contains 3 distinct contributions, whereas the first is what is commonly known as the dipole potential. It's proportional to the gradient of the local field intensity. So it is a high field seeking interaction. So it forces the particle to be trapped in the intensity maximum of the tweezer. And that's exactly what we use for tweezing the particles. Then we have a second contribution that is quadratic in the electric field, which is also local. So it only depends on the electric field at the position of the particle for which we calculate the force. And that's the radiation pressure force. So that's the back reaction of light scattering on the particle due to momentum conservation. And the third contribution that we get, that is now non-local in the electric field in the sense that it depends not only on the electric field of the particle that we are interested in, but also on the electric field at the position of the other particle. And these two are connected by the electromagnetic Green's tensor. And that's exactly the optical binding interaction. Looking at this equation, we can interpret this interaction as the interference, as due to the interference of the scattered field of particle 2 with the trapping field of particle 1. So it's not that the two scattered fields or that the scattered field directly exerts a radiation pressure on the particle. It's rather the scattered field modifies the local field seen by particle 1, and that leads to an effective interaction. So let's look at this interaction a bit more closely. So I spelled out the Green's tensor for you to make an important point. So this interaction, as we just saw it, so that's the force acting on particle 1 due to the presence of particle 2. And that force is quadratic in the volume of the particle and the susceptibility. And it's proportional to the real part of the electric field at particle position 1, Green's tensor from 1 to 2, and electric field at position of the particle 2. And it's the gradient of that. Given that the Green's tensor is a complex valued quantity and we take the real part of the entire thing, it immediately follows 3 important consequences: that this interaction is non-reciprocal, in the sense that it seemingly violates Newton's third law of action equals reaction. It is not conservative. It's conservative only for particle 1 if the position of particle 2 is held fixed, but as an interaction. It's a non-conservative interaction, and it can be interpreted as being due to light interaction. So being non-conservative and non-reciprocal means that it violates the conservation of total momentum, and it violates the conservation of total energy. But that's not a problem, because our system in reality doesn't consist of the two particles alone, but of the two particles and the light field. And what we did in this calculation here is we sort of traced out the light field. So the missing momentum and the missing energy is carried away by the light field. And that's why it's okay for the two particles in a purely classical picture to show these seeming violation of Newton's laws. Now, let me concretize this interaction for a particular situation that was then also realized in the lab by Ulrich Delić and Markus Aspelmeyer. Now, we now look at the situation of having two identical tweezer traps, which are highly focused. We have the particles trapped at the center of the tweezer traps with frequencies omega-1 and omega-2. The tweezers are at a distance d0, and the two particles, we only consider the motion of the two particles along the tweezer axis. The other 2 degrees of center of mass, degrees of freedom of the particles can be ignored for now, because the frequencies are sufficiently far detuned so that they don't couple to the motion along the tweezer axis. Then in this regime, we can spell out the equations of motion of the two particles. And what we get in the presence of gas damping is this type of equation of motion. So we get the equation of motion of a harmonic oscillator, which is coupled to a second harmonic oscillator. Now, importantly, this coupling is characterized by 2 distinct coupling constants, GR and GA, where GR is the reciprocal coupling constant, and GA is the anti-reciprocal coupling constant. And that's exactly the violation of action equals reaction, that the anti-reciprocal coupling constant appears with a plus in one equation of motion and with a minus in the other equation of motion. So the coupling constants between these two particles are not identical. Importantly, these coupling constants can be tuned experimentally. So the relative strength of these coupling constants is set by, so it varies with the cosine of k times distance, as well as with the cosine of the relative phase between these two tweezers. What that means is, by tuning the distance and by tuning the phase, the relative phase between the tweezers, we can tune the way that the scattered field interferes with the local trapping field on the other side. In particular, we can choose, for instance, that GR or GA are 0, so we can tune both of them to 0, and we can also individually, and we can also tune them such that they are identical, meaning that we have unidirectional coupling, right? So the GR minus GA vanishes while GR plus GA is still there, and we have complete freedom experimentally in tuning that. Looking at these dynamics, we see that it's characterized by a non-Hermitian Hamiltonian in the two modes, and this non-Hermitian Hamiltonian is characterized by a number of different regimes. So we have the blue region is the region where the coupling is predominantly reciprocal. The green region is the region where the coupling is predominantly anti-reciprocal. And in this regime of predominantly anti-reciprocal coupling, one can enter a time reversal broken regime where 2 exceptional points arise and one gets normal mode attraction between them, as can be seen here in the eigenfrequencies of the non-Hermitian Hamiltonian. So we'll come to that. I will come back to that a bit later. Now let's look at this. Let's look to Vienna and to the experimental realization of what I just explained. So in the experiment, the team of Ulrich Delić initially used a SLM to generate 2 tweezer traps through a microscope objective. The particles were levitated and their scattered light was detected. And a typical power spectrum of the scattered light includes two peaks, and these two peaks can be attributed either to the common mode, where the two particles move in the same direction, or to the breathing mode, where the particles move against each other. Now, the first thing we demonstrated is that in the case of perfectly reciprocal interaction, what we get is an avoided crossing when tuning the relative frequency of the two tweezer traps. So let me walk you through this. Here you can see the power spectrum, so the PSD, as a function of frequency, as a density plot, as a function of frequency, and as a function of relative tweezer power in the two traps, which determines the trapping frequencies. And what we get is, in case of perfectly conservative and reciprocal interaction, we get an avoided crossing, and the strength, so that the normal mode splitting is characterized exactly by the optical binding coupling constant that couples the two modes. We can tune this coupling constant with a distance. So in the diamonds are the dots are the experimental data, and the solid lines are the theoretical expectations. And that's both for perfectly reciprocal interaction. One in the case of having an attractive interaction for delta phi equals 0, and for having a repulsive interaction for delta phi equals pi. And you can see that the experimental observation agrees reasonably well with the theory. Now, let's look a bit closer at the mode dynamics. For that, we transform into normal mode coordinates and in a co-rotating frame. And we just consider the case now that the reciprocal coupling is 0, and we tune to perfectly anti-reciprocal coupling. Then we find in this normal mode picture that the dynamics are described by a non-Hermitian Hamiltonian, which is given here. You can recognize again that on the off diagonals, you get either the sum or the difference between the reciprocal and anti-reciprocal coupling constants. And then you can find that in this picture, when you tune the strength of the anti-reciprocal coupling constant versus the detuning of the mechanical frequencies, you can find again that there's a phase that is time reversal symmetric and a phase where the time reversal symmetry is broken. But if you look a bit closer, then in the time reversal symmetry broken phase, another phase arises, and that phase can be associated with a mechanical lacing phase. And why that's the case, let me explain it to you graphically. So initially, I briefly explained this picture of how that we usually have of a particle that is harmonically trapped scatters photons. So the particle is harmonically trapped in its potential with frequency omega naught. And when it scatters photons, it can either really scatter them elastically, so the frequency of the scattered light is the same, or it can scatter into the Stokes band omega L minus omega naught, or into the anti-Stokes band omega L plus omega naught, where the energy increase of the photon comes from an energy reduction from the mechanical motion and vice versa. Now, in our scenario here, we have two particles which would do that symmetrically between Stokes and anti-Stokes band independently. However, they are coupled, and they are coupled through interference of scattered photons. Now, if the tweezers which are illuminating the two particles exhibit a phase shift of exactly pi-half, and the distance is chosen appropriately, then this means that this picture can be transformed into new normal coordinates, which are a complex linear combination of the two old normal coordinates, which are chosen exactly such that now, in one case, the anti-Stokes scattering process is suppressed in comparison to the Stokes scattering process, while in the other case, it's exactly vice versa. And this leads to the fact that one of the two complex normal modes now exponentially increases in amplitude, while the other exponentially decreases in amplitude. Now, what happens if this normal mode here exponentially increases in amplitude is that eventually it will leave the regime where this linearized description is valid. And that's exactly when the mechanical lasing occurs. If this linearized description ceases to be valid, the first nonlinearity that starts mattering is the nonlinearity in the optical binding interaction, which itself is again anti-reciprocal. One can then transform the set of coupled equations, the coupled equations of motion, to an effective equation of motion for the mean amplitude of the mechanical motion and the relative phase between the two mechanical modes. It's described by a nonlinear differential equation, which includes a function that is given by first order Bessel function over x. And this equation now exhibits a Hopf bifurcation. So it exhibits two steady states for certain parameters, in particular for parameters which are in this regime. One steady state is that the amplitude is exactly 0, and the other is that the amplitude is finite and large. Let's go to the experiment. Again, Rudolph, Delić, and co. implemented this scheme in the setup. So they trapped the two particles again. They tuned all parameters such that they are only coupled in the anti-reciprocal way. So theta is here the relative polarization between the two, is the polarization angle, but that's not relevant for what follows, just to mention it. And now they reproduce the theory expectation of where we expect the exceptional points to lie and where we expect the Hopf bifurcation to occur. So left, you can see the theory prediction that we had on the previous slide. Right, you can see the experimental data. Now let me show you some details from this experimental plot. So D and E here are the first order correlation function of the amplitudes of the two different modes in the time reversal symmetric phase, in the time reversal broken phase. You can see here an oscillatory decay, while you can see here a bi-exponential decay. That's also a clear signature of having entered the time reversal broken phase. And then we can also run a scan by tuning the anti-reciprocal coupling going along the dashed line from bottom to top. And we can see the Hopf bifurcation occurring at the parameter anti-reciprocal coupling over gamma approximately 0.5. So in red, you can see the theoretical expectation, and the red circles are the experimental data. You can also look at a horizontal cut through the plot, and then you can nicely see the exceptional points and normal mode attraction. You can also see that the mean amplitude of the two motions is always 0 unless you enter the phase inside the Hopf bifurcation. And when you look at the amplitudes of the two particles and plot it in a 2D plot, then you can see in a PT symmetric phase that it is a Gaussian centered at 0, while in the time reversal broken phase, but outside the Hopf bifurcation, still centered at 0, but skewed. While as soon as you enter, as soon as you go into the, as soon as you approach the stable limit cycle phase, you get a finite amplitude, and the particles move at a mean amplitude that is not 0. Now, with that, I would like to finish the part on the classical optical binding and come to our recent work on the quantum theory of optical binding interactions. Now we take a step back and ask ourselves the question: how would this interaction actually look like when the two particles are deep in the quantum regime and quantum effects really become necessary? Because so far we only considered classical forces arising from integrating out Maxwell's stress tensor, and so everything could be understood in a perfectly classical sense. Now the situation that we are interested in is now we have a bunch of particles. Each particle has degrees of freedom, center of mass motion, and its orientation. So that's 6 degrees of freedom. Each particle is characterized by a dielectric permittivity function, which we assume to be homogeneous inside. And these particles are subject to some external laser field. And they can exchange information via light scattering. So for now, we treat the electrodynamic degrees of freedom actually as a degree of freedom. So we will derive the total Lagrangian that describes the coupled motion of all mechanical degrees of freedom and of the light field in presence of external driving. And in order to do that, we first need to realize how is actually the internal polarization field related to this to the electromagnetic degrees of freedom, and how does the interaction Hamilton Lagrangian actually look like? And for that purpose, we first write down the total electric field. And we do that in the Coulomb gauge. So the total electric field separates in a transverse part and a longitudinal part, where the transverse part is given by the incoming field as well as all transverse outgoing fields, or all transverse field degrees of freedom, plus some longitudinal part, which is due to the induced dipole moment inside of the particle at position S, and it's integrated over all volumes of the particles, and the corresponding longitudinal electric field at position R is then determined by the electrostatic dipole Green's tensor, which is given on the right. Now, this internal polarization field is, however, not independent of the electric field at this position because of the constitutive relation that the proportionality is given by the dielectric permittivity. It's a function of position. Now, plugging this into the above equation yields an integral equation for the total electric field. And this integral equation for the total electric field must in principle be solved to know the field at all positions and in order to calculate the electromagnetic forces and torques. Now, this integral equation can be solved symbolically by introducing an integral kernel. And one finds that this electric field is driven, or it is given by an integral over all space of this integral kernel, which itself fulfills an integral equation, which might be difficult to solve. Then it's proportional to the transverse incoming field as well as to the field degrees of freedom, a time derivative of them. Now, don't give the equation for the integral kernel. Suffice it to say that the integral kernel can be explicitly calculated in the regime of Rayleigh scattering, where the dielectric particles are much smaller than the wavelength characterizing or the length scale characterizing the incoming electric field or laser field. With this expression, one can find it then derived. That's another complicated step. So if you're interested in details, please check out our archive. But given this integral kernel, one can formulate the interaction Lagrangian for the light-matter interaction. And it takes this form. It's an integral over all space twice. It's the transverse part of the electric field multiplied with the integral kernel and this susceptibility prefactor, and then again the electric field at position S. Now, the electromagnetic field degrees of freedom enter through this A, and the particle degrees of freedom, so the degrees of freedom of all particles, enter through this dielectric function, because this dielectric function depends on the particle. So the spatial dependence of this dielectric function is determined by the position and orientation of all particles. So that's a very complicated dependence. That's why it's not explicitly given. But in principle, this can be calculated. Now that's a big step. What we do next is we quantize this theory, and we trace out the electromagnetic field degree, first, we do something else. We rewrite this interaction Lagrangian for small particles and large separations between the particles you write this interaction Lagrangian via a mechanical gauge transformation in the following way. We write it as a sum of some external potential. This external potential contains the tweezer trap, so that's just the dipole potential that we also had initially and on one of the first slides. And it also contains a interaction between the two particles, which is static in the sense that it only depends on G naught. It only depends on the electrostatic Green's tensor. So that's not the same interaction as we had previously in the optical binding. We had the full Green's tensor. So that's only the electrostatic Green's tensor. But then, in addition, we get the interaction between the electromagnetic degrees of freedom A and the particle degrees of freedom. And this interaction now takes this form. And now the dependence on the particle coordinates is here in these integrals over the particle volumes, which of course depend on where the particle is and how it's oriented. Now we quantize the theory and trace out the electromagnetic degrees of freedom in the Born-Markov approximation. I spare you the details. What we get in the end is a Markovian quantum master equation for the mechanical motion of all those particles. And it contains a couple of contributions. So it first of all contains a coherent unitary dynamics, which is just the free motion of the particles. Then we get an optical potential, which now contains the local trapping potential, but it also contains an interaction which now depends on the full electromagnetic Green tensor, but it's not the full optical binding interaction, it's only the conservative part of that. So why is here not G naught, but G? That's exactly the lamp shift. So the lamp shift is responsible for including the full field propagation into this interaction, at least the conservative part. So where's the non-conservative part of the optical binding interaction? Well, that's hidden in these Lindblad operators. And these Lindblad operators are given by the sum of all scattered fields. So that's essentially the sum over the field scattered by each of those particles. So we sum over all particles, we have something which is proportional to the electric field at the position of this particle, and it's proportional to a momentum kick of strength K naught, which is the wave vector of the incoming light field. And these Lindblad dissipators, they not only lead to decoherence and noise, they also lead to a non-vanishing expectation value on the level of the Ehrenfest equations. And this is exactly the non-conservative optical binding interaction. So let me make things simpler again by simplifying it for the situation that we had experimentally. So again, we have two deeply trapped particles, and we only consider the motion along the tweezer axis. Then again, we have H naught, so that the dynamics of these two particles contains two unitary contributions. One is H naught, which is the free dynamics, so the motion in the harmonic potential. Then we have one coupling term, which is given by the reciprocal coupling constant. So that's exactly the conservative part of the interaction. And then we have a Lindblad dissipator, which is now not only a shot noise heating momentum diffusion term, but it also contains contributions where J and J prime are not the same. So here should also be a sum over J prime, by the way, because these diffusion coefficients have off-diagonal elements. And these off-diagonal elements of the diffusion coefficients, they have an imaginary part, and this imaginary part is exactly given by the anti-reciprocal coupling constant. So that's the part that gives rise to the non-reciprocal interaction that we also obtained in a classical picture with a completely different interpretation. Importantly, this part here, this real part of the diffusion coefficient 1 and 2, that gives rise to correlated recoil heating between the two particles, which is physically maybe not surprising, but it would not have been possible to obtain this expression from a purely classical theory. So that's really now where the quantum treatment becomes unavoidable. Now, when you plot the relative phase between the two tweezers versus the distance between the two tweezers and look at which type of interaction dominates. Then again, in blue, we have predominantly reciprocal interaction, green, predominantly anti-reciprocal interaction. But then we also get a regime where we have mainly directional interaction, so where the direction points strongly into one of the two directions. And in the center of this plot, we get a situation where none of those things dominate, where the interaction between the two particles would vanish classically. But the motion of the particles is not uncorrelated because of recoil correlations. And that's so due to quantum noise correlations acting on the two particles. And that's a quantum signature of optical binding. Now, there's a very important note. This master equation that I formulated above, it can always be rewritten as, or it can always be interpreted as the ensemble average over a stochastic feedback quantum master equation, which contains only local operation and classical communication. So it's a feedback quantum master equation which contains only measurements on particle 1 and particle 2, which are independent, and then acts forces on the two particles. What does that mean? So it means that this interaction can always be interpreted as an LOCC channel, and as a consequence, there can never be entanglement due to free space optical binding. And that's really an important insight. So it tells us that no matter what you do, if you just have two particles levitated in vacuum and interacting through scattered lights, this can never generate any entanglement. But knowing under what conditions you cannot achieve entanglement allows you to circumvent these conditions. And there are three ways you can circumvent this. First, you can enhance the coherent interaction over the incoherent interaction by adding, for instance, Coulomb interaction, by charging the particles. So this can be a strong channel for coherent interaction, which can then surpass the limitations of the scattering that is inherent to optical binding and which is responsible for the loss of coherence. Then you could feed squeezed light onto the particles. That's a proposal by Carlos González Ballestero from a group of, or who was in the group of Oriol Romero Isard, where they showed that recoil heating can be suppressed via input of squeezed light, much like in macroscopic optomechanical oscillators. And the third strategy is to enhance the coherent interaction by adding a cavity to the setup. So recycling the scattered light, which otherwise would lead to decoherence, to enhance the interaction. Now, let me use my last 5 minutes to briefly explain the first and the third alternative, because that's what we have been working on. Now, in this paper, we consider two particles trapped in optical tweezers, like we had it as we had it in the experiment before, and we propose to charge those two particles, so to add Coulomb interaction to the picture, and then implement a feedback loop by detecting the backscattered light via homodyning and using the detected signal to apply a homogeneous force across the two particles, which is designed in such a way that the stationary entanglement is enhanced of the state. Now, the measurement by homodyning, the measurement signal of the two deeply trapped particles is just the expectation values of these particles plus noise, and the stochastic feedback quantum master equation that describes these dynamics, that's a nonlinear stochastic master equation, which contains decoherence due to recoil heating, all sorts of interactions between the two particles, including Coulomb interaction, and the feedback forces. And importantly, these feedback forces, they act as homogeneous forces on the two particles, and the strength is chosen as a function of time depending on the measurement record. So that's an e to stochastic integral, which depends on the measurement record of the two particles. And HS is a filter function that is applied, which is chosen in such a way that the particles are cooled and the stationary entanglement is enhanced. I will spare you the details. Let me just mention that for feedback schemes that have been implemented successfully in the past, stationary entanglement can be realized under realistic conditions, challenging but realistically, and as signified here by the logarithmic negativity. And having such a system can also be used for differential force sensing, because the motion of the differential mode of these two particles strongly depends on the presence of external force gradients. Then that's that. Let me now briefly say a few words about the other strategy to enhance, to generate entanglement via light-induced interactions. So the first alternative was actually entanglement through Coulomb interaction. So that's actually cheating. Now the second alternative is now really entanglement through optical interactions. And that's now, we look at optical binding through a cavity mode. So in this case, the particles can be really far apart. In the other case, we had optical binding interaction decays as 1 over kd. That's due to the free space mode. Replacing the free space modes with a cavity mode, we can also move the particles far apart. And the situation is the following. So we have two particles trapped. Okay, so that's again a theoretical proposal, but the situation that we propose is two particles trapped in the coherent scattering configuration. So we have two tweezers, each holding a particle and a cavity around them. And the motion of those particles scatters photons into the cavity mode, which then becomes populated. And since both particles interact via the cavity mode, you can implement an interaction between the two particles in this way. And this interaction can be linearized, and the Hamiltonian of the system is some harmonic degree of freedom due to the cavity mode, the two mechanical oscillators, and linear coupling between both oscillators and the cavity mode, but no direct coupling, because we now assume that the particles are sufficiently far apart so that the direct optical binding interaction and Coulomb interaction do not matter. Then entanglement can be generated or heralded in this situation in the following way. The particles are first prepared in the ground state, then the detuning is swapped to the blue sideband. A Stokes scattered photon is detected, which conditionally prepares the state in an entangled state because you don't know which of the two particles has been excited. Then the detuning is switched to the red sideband, and the anti-Stokes photon can be detected afterwards. Then there's a bound on the flux of anti-Stokes photons that you would expect from classical under classical conditions. And whenever you observe that the flux of anti-Stokes photons, so that's the black line here, exceeds the classical bound, that's the red line, then you demonstrate that the two particles have indeed been entangled. Now, two things to mention at this point. First of all, this scheme has been proposed for clamped optomechanical schemes quite a while ago already, and it has also been successfully implemented for clamped optomechanical systems. In our proposal here, we show how it can be adapted to a levitated situation. And also maybe interesting to know is that this setup of two particles that are trapped in tweezers and which speak to each other via a cavity mode has been recently implemented in the lab of Lukas Novotny at ETH in Zurich, and they are currently working towards observing quantum signatures of the interactions of these particles. With that, I come to the end of my talk. I briefly summarize, so I try to explain to you why optical binding is non-reciprocal. I explained the classical theory of how optical binding comes around, and summarized the recent experimental efforts by the team of Delić and Markus Aspelmeyer. I summarized the quantum theory of optical binding, and we briefly talked about entanglement generation via cavity or feedback interaction. With that, I want to thank you for your attention, and I want to thank my collaborators, particularly Henning Rudolph at the University of Duisburg-Essen and Delić at the University of Vienna. Thank you very much.
Thank you very much for the very nice and inspiring results. The floor is now open for questions. Okay, I can start. So yeah, I have a question about the classical results where you describe the transition into a limit cycle, the Hopf bifurcation, the diagram that has the Hopf bifurcation in there. I was just now wondering, now in this so once, how should I imagine now this mechanical lasing part? Because there is I think there is something that is slightly unconventional here. For a single particle, if I will imagine now a single particle in some nonlinear potential, I could imagine that in this region there will be some form of a frequency comp popping up in this region, because now the system will start having new frequencies as it's in this phase. Now, when I have the two particles now forming together this bound state at in some way, it's in this mechanical lasing. How should I imagine this now?
Yes, so it's certainly unconventional. I agree. I should have maybe worded it a bit more carefully in the paper. We actually also say that it's we see the arising of a stable limit cycle, which shares similarities to mechanical lasing transitions. So that's I think the more precise wording. Okay. So what you get is simply by exponentially enhancing one of those two modes, it starts exploring non-linearities of the potential, and or non-linearities of the equations of motion, let's put it that way. And in our case, these non-linearities are due to various reasons, but the most important one is due to the optical binding interaction between the two particles. But no matter what this non-linearity is, it can give rise to a stationary, it can give rise to a Hopf bifurcation, and therefore also to the existence of a stable limit cycle. So a stationary amplitude that is non-zero, and that situation is also related to, for instance, a decrease in the width of the power spectrum. So that's the similarities that we mean. But yeah, so it's not exactly the same as in other systems, but it's one of the unique features of the system, right? I mean, the interaction in our case is non-reciprocal, really, also in a non-linear regime. It's really it fundamentally does not fulfill Newton's third law. Yes.
I understand, and just one short follow-up question. Here now in the panel B, this looks like well, it's a frequency, or is a detuning sweep, and the amplitude is tracked. Should I expect, I guess, because of the nonlinearities, this makes sense, that there will be coexisting solution branches on some regime. So I will expect some hysteresis cycles that could be going on. Is this something that it's observed or is expected?
I'm not 100% sure now, but as far as I know, yes. So I should have probably mentioned, so this line here where this Hopf bifurcation occurs, that occurs when the effective when the heating, the exponential increase rate exceeds the effective damping rate, right? So that's really when the trajectory starts exploding over all bounds, and then of course it depends on from as you say.
Okay, great, thank you so much. So I think Clara has a question.
Yeah, thank you very much for the exciting talk. I was wondering about time reversal symmetry. You mentioned the broken time reversal symmetry a few times, and in particular how it is defined in this context, and then how it is related to reciprocal and non-reciprocal interactions. So the reason why I'm asking is, at some point you showed also a phase diagram where you showed that actually the non-reciprocal and reciprocal phases, for example here, but there was also another diagram where you showed it as a function of distance between the two particles and phase. And so I was quite surprised that you said that I would have that the reciprocal phase was really extended over an entire area or over a certain interval of phases. Whereas I would have expected that it's maybe so if the let's put it like this, if the broken time reversal symmetry is an interference effect which depends on the distance, then I would have expected well, maybe you have some intuition on how this is connected. So how
I'm not 100% sure because
before I start babbling.
Yeah, so that's a lot. So this question is a lot about terminology. So I'm not 100% sure because I'm not 100% sure whether everyone uses the same terminology on these things. But in the present case, the Hamiltonian, the effective Hamiltonian that describes this interaction. So if we leave damping aside, that is time reversal symmetric, right? Mm-hmm. And you can enter time reversal symmetry broken phase in the regime where the eigenvalues get a finite imaginary part. And that's exactly what we mean here. So that's really time reversal symmetry in the sense of reversing time, so really physical time. Okay. Whereas parity symmetry is always broken because the two particles experience different tweezer phases locally, so that they are different. Of course, if you swap everything, including the tweezers, then it's symmetric again. Now, maybe what's important here to mention, I hope that answers the question partially, or
yeah. Mm-hmm.
So what's maybe important here to mention is that it's something that I'm also myself not 100% certain about, but so a difference to so what in our case, it's really about the interaction itself being non-reciprocal, right? Mm-hmm. So it's not that the propagation of electromagnetic fields is non-reciprocal, or mm-hmm. Susceptibility is non-reciprocal. Mm-hmm. And one so for instance, the propagation of electromagnetic fields, reciprocity of that does not necessarily imply reciprocity of the interaction if the interaction is nonlinear in the electric field. And that's the case in our case. So in our case, really what is relevant, or what is the cause for the non-reciprocity, is interference of the field. Mm-hmm. Yeah. So that's not necessarily related to this notion of non-reciprocity that people have, for instance, in clamped optomechanical systems where the interaction mm-hmm. is always linearized. Yes, so it has a slightly different origin.
Mm-hmm. I see. Yeah, I was thinking, for example, in these reservoir engineering approaches, there you can understand non-reciprocity as an interference effect between different paths. And here I was wondering if there is a possibility of mapping this to this picture. Because, your light field is a bit like this third mode. And then you would think of maybe the time reversal symmetry breaking term as, like a synthetic gauge field. And so I was wondering if there is a way to map this.
Yes, so there is a way of mapping this, and this can be seen from this master equation here. So you can see here you have a coupling in the between the 2 degrees of freedom mm-hmm. Through the Lindblad dissipator with an imaginary part, and that's exactly what those people from reservoir engineering, what you normally get in the situation of reservoir engineering. So you can have this interpretation, but that interpretation only holds in the linearized regime, whereas our non-reciprocity extends beyond that. So we usually have this physical interpretation, but you can draw the links. Yeah, but I personally don't find it so helpful, to be honest. But because of my personal trajectory, I'm used to the other way of thinking about it. But yes, but you can draw these links certainly.
Okay, very interesting. Thank you very much for elaborating.
Is there any more questions from the audience? Well, if not, let's thank the speaker again. And and thank you all very much for joining us today. Thank you, Benjamin.
Thank you very much for coming.